this is a kinetics practice problem. It also connects some pulley kinematics as well. The question is, determine the required mass of block A so that when it is released from rest, it moves the 5 kilogram block B a distance of 0.75 meters up along the smooth inclined plane in t equals 2 seconds. Neglect the mass of pulley and the chords. In this problem, do we have to do impending motion? The answer is no, because we have a smooth inclined plane, so we don't have any friction. And so that means based on the dynamics, there has to be some motion. There's nothing to stop the motion from happening. So we'll start off this problem by defining our position coordinates and our free body diagrams. So for block A, I'll define the distance of block A to be like this. And then I'll do block B down the incline like this. So this is XB. So I'm actually doing different coordinate systems for block A and block B. When I draw the free body diagram of block A, I have block A here, and it is actually attached here by not just this one cable here, but up here you can see that there's 1, 2, 3 cables. So even though it's attached to this pulley with just one cable, there's actually the force of 3 cables pulling block A up. So the force up from block A will be 3T. So it'll be whatever the tension in that cable is times 3. Then we'll also have the weight of A coming down. This is the free body diagram, the kinetic diagram, and they want block B is moving up the incline. And so that means that block A has to be moving downwards. So here you would have mass of A times the acceleration of A going downwards. Note here that I've defined the acceleration of A downwards, positive down, and that matches the positive down of the XA from our kinematics drawing. For block B, here we have block B, we have block B. Note this is a completely different diagram for block B. Now we have a normal force from the incline on B. We also have the tension in the cable pulling it upwards. And then we also have the weight of B pulling it down. So those are all the forces on B. When we draw the kinetic diagram of block B, and this is very, very important. We know that block B is moving up the incline. It tells us right in the question. Where is that? Yeah, it moves 0.75 meters up along the incline. So it's very tempting to say mass of B, acceleration of B. However, up here, we defined xb, the position vector, as going down the incline, which means we have to match that here. Otherwise, our equations won't work out. So we know that our acceleration b is going upwards, so we'll be expecting a negative number, but we still have to define the position. We're still going to say mass of b, acceleration of b. So you have to make sure that this arrow here that's denoting your acceleration is moving in the same direction as this position vector here. That's very, very important, even though you know that the B block is moving up the incline. So now we'll do our kinematics equations. So we've got one rope, and the rope sort of starts here at the center of that pulley, goes around, up, and back down. So the length of that rope will be 3 times XA plus XB equals constant, 3 VA plus BB equals 0, and then 3 AA plus AB is equal to 0. This is our first equation that connects the acceleration of A with the acceleration of B. The information provided in the question is that delta xb is equal to 0.75 meters and t is equal to 2 seconds. Since we don't have any external forces on our system that we know are changing with time, we can assume that we have constant acceleration here because we essentially have a system that's being driven by gravity. So we can assume constant acceleration, which means we can use our constant acceleration equations. So I'm going to use this one. X is equal to x naught plus v naught t plus 0.5 at squared. Because we already know, our delta x, which is x minus x naught. We know our v naught is equal to 0 because our system starts from rest, and we have values for t is equal to 2 seconds. So we can actually find our acceleration b right away from this equation. So we end up with xb minus x naught b equals 1/2 abt squared. And then from here, we find out that AB is equal to negative 0.375. That's what we were expecting because we knew that it's moving up the incline, but we had to define our positive direction going down. So that makes sense. So our AB is equal to 0.375 meters per second squared up the incline. From our equation here, AA plus 3AA plus AB equals 0, we can find AA. Now we have the acceleration of A is equal to 0.125 meters per second squared. Now that we've done our kinematics, we go back and do our kinetics. So I'm going to move this up a little bit here. Here we have our free body diagram and our kinetic diagrams. So remember that these drawings are representing actual equations. So these drawings are equal to each other, and if I write this out as an equation, for the first one we have the summation of Fy is equal to the mass of A times the acceleration of A in the y direction. Down here we have the summation of Fx is equal to mb times the acceleration of b in the x direction, and then we have the summation of Fy is equal to mb times the acceleration in the y direction. So from these two drawings, we actually have three equations because block B has components in the x and y direction. Our unknowns are the mass of A is unknown, the normal force B is unknown, and the tension in the rope is unknown. So we have three unknowns and three equations, and we can solve this problem. So when we fill those out, we'll start with block B because we know the mass of block B and the acceleration of block B. So for block B, we've got summation of Fy is equal to mb acceleration of b in the y direction. But what is the y direction? We didn't define a direction for y for b yet. And so the y direction would be perpendicular to the x direction. So if we set our x direction for b here, which is what we defined previously, our y direction would be going upwards like this. Now, because we have a normal force b here, that means that our block isn't floating. If our block lifted off of the slope, there would no longer be a normal force on that block. But also, our block isn't floating. Blocks never float in this course, so they'll never be, if you have a block sliding along a plane, and this is your x direction, we're never going to have blocks lifting upwards, which means that the acceleration in the y direction will always be equal to 0. So in this case, it's also equal to 0. So this is saying that our summation in our forces in the y direction will be equal to the normal force going positive minus the weight of B cos of some angle will be equal to 0. So we need to figure out what that angle theta is. And one way to do that is we know that we have the slope here. The angle of the slope is 60 degrees. And we know that our mass is going downwards completely vertically, and that our y direction is perpendicular to our slope. So our y direction is there, and this is the direction of our weight. So if we draw a triangle, we can actually just draw it, we'll extend, this is the direction that we need, so I'll just extend the direction that we need to project it on, and this is the weight that we're trying to project. So we'll make this weight here our hypotenuse, which means we'll connect our triangle here. If this is 60 degrees and this is 90, that means this angle is 30 degrees. That means that this angle is 60 degrees. So then if we do weight times cos 60, that will be our magnitude of this piece of the triangle here, and it's going in the negative direction as expected. So when we plug this back in, we would say, oops, sorry, dropped my pencil. We have normal minus the weight of B cos of 60 is equal to 0. There's a lot of different ways to visualize these triangles, but this is like absolutely critical to be able to come up with these angles. It's really, really, really important. So here, from this equation, we know the weight of B, we know our angle, we can solve for our normal force. So our normal force is equal to mass of B, gravity, times cos of 60. I'm going to move this up now. Actually, no, we still need our drawings. So then we have summation of Fx is equal to mass of B times the acceleration of B. Now this is the acceleration going along the slope, so it's the entire acceleration of our block. And the forces that we have, you can see we have the tension of the cable pushing upwards, pulling it up the slope, and then we have again a component of this weight. So we will have negative T plus the weight of B sine of 60, because now we're looking at this component of our triangle, so that's sine 60. And this would be equal to the mass of B times the acceleration of B. We already know the acceleration of B from our kinematics. We know the mass of B, therefore we know the weight of B, and we can solve for T. That's our second unknown solved. Our T works out to 44.35 newtons. And then I'm going to scroll up just to show you the drawing. Then we had 3T moving upwards minus the weight of A is equal to the mass of acceleration going down. So I'll write that equation out quickly. So then we have 3T moving upwards minus the mass of A times gravity is equal to the mass of A times the acceleration of A. We already know acceleration of A, we know the tension, and then we solve for the mass of A, and mass of A is equal to 13.7 kilograms.